Okay, let's talk about bond length and bond angle. Alright, so we talked a little bit about the idea that depending on what kind of hybrid orbital you have, there's a different amount of percent S content in your hybrid orbital. And that means that you get to see more nuclear charge or less nuclear charge, depending upon whether you have more or less S content. Okay, so looking at the molecules here, C2H6, C2H4, C2H2, you have a single bond, double bond, and triple bond. That means that the carbon over here is an sp3 hybridized carbon. The carbon over here is an sp2 hybridized carbon, and the carbon over there is an sp hybridized carbon. You could also rise to that conclusion by looking at the directions. 2 directions, 3 directions, 4 directions. Alright, now, in an sp3 hybridized orbital, you only have 25% s content because there's only one s orbital out of 4 orbitals. In the sp2, you have 33% s content because there's one s orbital out of 3. In an sp, you have 50% s content. Now, notice something interesting about these molecules. First things first, the bond lengths. The bond length of the carbon-carbon bond is longer for a single bond than it is for a double bond. We go from 1.54 angstroms down to 1.34 angstroms. And when you switch over to a triple bond, this decreases even further to 1.20 angstroms. So there is a decrease in the bond length as a result of the fact that your orbital is greater in content. Your s orbital is 50% in content for sp hybridized orbitals, so they get to see a lot more of the nuclear charge, and as a result of that, their atomic size decreases, or in this case, the bond length decreases. And you can kind of see that to lesser extent for the carbon-hydrogen bond to which the carbon is connected to. If the carbon is sp3, that has less tendency to be attracted towards the nucleus, so the bonds tend to be a little bit longer. This is 1.10 angstroms for the carbon-hydrogen bond, 1.08 angstroms for this other carbon-hydrogen bond, and by the time we get to the sp hybridized carbon, the carbon-hydrogen bond goes down to 1.06. It's a very subtle change, but it is a noticeable experimental change. Now, what we can actually do though is the following. So we know now that triple bonds are going to be the smallest ones out of the bunch. Double bonds will be intermediate in size, and single bonds will be the longest ones. But it turns out that depending on the hybridization of the carbons sandwiching single bonds, you are going to affect how long the actual bond length of that single bond ends up being. So not all single bonds are the same. Okay, and first thing that we want to make very clear when we look at a molecule like this is that, okay, we're going to look at which single bonds are going to be longer, which ones are going to be shorter, but regardless of what single bond you're looking at, a single bond will never be smaller than a double bond. The double bond is still going to be smaller than a single bond, but a triple bond is going to be smaller all the time than a double bond. Okay, so out of all the bonds, the smallest one will always be the triple bond. Out of all the bonds here, the next smallest one will be the double bond. But with that being said, you can start looking at the single bonds, which I've highlighted in, with the arrows over here, in order to determine what the order is, the order of increasing bond length. You have to look at the interactions of hybridized orbitals for the carbon sandwiching the single bond. Now in the case, and this is actually a very simplistic way to go about it, in the case where you have a single bond between two sp3 hybridized orbitals, each one of them contributes 25% s content. So if you add them up, if you literally add them up together, you're going to get 50% s content. If, on the other hand, the single bond is sandwiched between an sp3 or an sp2 hybridized orbital, you have 0.25 or 25% content and 33% content, giving you a grand total of 58% content. So as you can see here, this addition is giving you now a greater amount of s orbital content within the single bond. And now, if that single bond is sandwiched between sp2 carbons and sp2 carbons, Now you have a grand total of 66% S character. sp3 and sp, now that's very interesting because having an sp2 and sp2 is good, it's better than sp3 sp2, but it's not as good as having a single sp, because even with the worst case scenario, which is the sp3 hybrid orbital, sp3 plus sp2, you end up with 75% s content, and thereafter this gets better and better. sp2 and sp 83%, sp technically 100% content. And so the higher this number gets, the more nuclear charge you get to see, and as a result the bond length is going to decrease. So what you want to do is, in order to determine the increasing order of bond length, you want to look for the single bond that is sandwiched between two sp carbons, right? You're looking for this particular guy, and if you look carefully you can see here in the structure that this particular single bond is indeed sandwiched between an sp carbon and another sp carbon. So this is going to be the smallest one present in the molecule. The next one will have to be an sp2, a single bond sandwiched between an sp2 and an sp hybridized carbon. So for the sp, basically narrow down on these triple bonds. Triple bond, this carbon is sp, and the carbon next door, as it turns out, is sp2. So this is the next carbon in the series in terms of bond length. So this is a little bit longer, but still pretty small. The next one in the series will have to be an sp3 hybridized carbon next to an sp hybridized carbon. And of course, you have to have a single bond sandwich between them. So once again, if you narrow down on the triple bonded carbons, which are all sp, this one is next to a carbon that has 4 connections, therefore being an sp3 carbon. So this single bond right here is going to be the next longest in the series, or the next longer one. After that, we look for sp2 carbons, and those will be usually the ones that have double bonds associated with them. So looking here, we have double bond, double bond, double bond, double bond. So we want to find out a single bond that's sandwiched between two sp2 carbons, and that one, if we look carefully, we'll notice right here, this carbon is sp2, but the one over here is also sp2, so that fits the criteria, and that's the next carbon in the series. Alright, moving on to the sp3 sp2, we find out that that particular single bond lies between these two carbons, this one being sp3 and that one being sp2. And the last one, of course, which is bound between an sp3 and another sp3 carbon, is the longest in the series, and that's the one shown right here at the very end. So as you can see, the bond lengths of all these different single bonds actually do differ depending on the hybridization, and the hybridization theory does a very good job of predicting whether certain types of single bonds are going to change in size in respect to each other. And it's kind of a nice, neat little way of looking at bond lengths in general. Okay, now one more thing to talk about, the bond angle. Much like we talked about the relationship of the hybridization with the bond length of the molecules, we can also talk about the bond angles that they have. We know that tetrahedral molecules have an angle of 109.5, and tetrahedral molecules tend to have sp3 hybridization. Trigonal planar molecules, which have sp2 hybridization, have an angle of 120. And sp hybridized molecules, which have triple bonds, tend to have an angle of 180. So what we see is that as the S content goes up, the angle goes up as well. And another way to put it is that the angle goes up when the percent P goes down. Alright, so increasing the percent P will decrease the bond length. And the limit is going to be about 90 degrees, since you have 90 degrees in each one of these P orbitals. Alright, now to exemplify what's happening, let's take a look at the 4 following molecules. At first look, you might say, well, I mean, aside from the overall polygon shape, there's no difference between in terms of hybridization, because this carbon here highlighted with the H's, actually drawn out, is sp3. Has to be sp3 because it has 4 directions. The carbon over here also has 4 directions, so it's sp3. This one is sp3 as well, and so is the last one. So you would say at first look that there's no difference whatsoever. But the problem is that when you look at the bond angles, you realize the bond angle inside that polygon is 60 degrees for the triangular shape, 90 degrees for the square shape. 108 degrees for the pentagon shape and 109.5 for the hexagonal shape. Now the reason why, technically you would say, well, wait a minute, shouldn't that be 120? And it should be, but this particular shape happens to be non-linear, decreasing the bond angle somewhat. But this one does the best job at approximating the true bond angle of a tetrahedral structure. So this is what we would call a true sp3 hybridized carbon. Now, as the bond angles get smaller, what we basically think of is that the percent P is going up. And for the percent P to go up, we are going to be decreasing the percent S as well. They're all sp3 from the point of view of the theory, but there is some extent to which, some of them are more sp3 than others. All right, so this is the way I want you to think about it. The 109.5, that's your true sp3 hybridization on the carbon. As the bond angle decreases inside the polygon, the percent P is going up. So I'm adding some amount, Z, Y, or X, whatever they are, they is greater amounts altogether. But because you have to have altogether 4 orbitals in content for your hybridization to work out, if you increase the amount of P, that will have to come at the expense of the amount of S. Okay, so notice that here we're adding some Z amount, here we're decreasing some Z amount. All right, now this is the interesting part about it. Okay, so the effect doesn't just apply to the carbon over here, or the carbon-carbon bonds rather, which are part of the bond angle, but it also can be applied to the carbon-hydrogen bond. Now the thing is this though, when I tell you that you increase the amount of p orbital, well, you only have 3 p orbitals in the carbon, so you can't just be increasing the amount arbitrarily. Where is that p content coming from? And it's actually coming from the neighboring atoms, the atoms that are outside of the ring. And so for the percent p to go up inside the ring, it has to basically come at the expense of decreasing the p content of the CH bond. But if you decrease the p content of the CH bond, you will increase the S content. Okay, so check this out. The S content of the CH bond is going to go up as you move from the hexagonal shape to the pentagonal shape to the square shape to the trigonal shape. So that means that, technically speaking, there's going to be some changes to the bond lengths. First of all, inside the ring, we know that the P content is going up from right to left. So the carbon-carbon bond lengths are actually going to be increasing, and that's kind of what we see. 1.536 goes up to 1.46, which goes up to 1.555, and then it kind of has a decrease for the trigonal shape, which I'll discuss later. For the carbon-hydrogen bonds, the S content goes up as we move to the left in the series, so we see that the bond lengths decrease from 1.119 to 1.114 to 1.113 to 1.083, implying that the hybridization is working out. And moreover, if you look at the bond dissociation enthalpy of the carbon-hydrogen bonds, you see that there is a nice progression in terms of numbers. Now, this one's a little bit longer because of the non-planarity shape of the molecule. But what you can see is that starting from the pentagon and moving over to the trigonal shape, there's actually a vast increase in the amount of energy required to remove the CH bond, or actually the hydrogen from the CH bond altogether. So you can see that hybridization plays a huge role in explaining reactivity.